Hello, everyone, and welcome to the first class in Florida Data Science Academy's 24-part series, Introduction to Data Science. I'll be your instructor, Dylan Sinnixon, and today in class one, we'll be going over all of the basics of RStudio. In particular, how do we write basic forms of code, and also how do we move throughout the interface. So the first thing that I'm going to do today is create a new R script. So to do that, I'm going to click on the File tab. I'm going to click New File, and then I'm going to move and click our script, and then you can see a new window opens up in the top left-hand portion of our screen. It's currently called Untitled 1. We haven't named it yet, and this is where we're going to write our code, and then we're subsequently going to save this code. So the first thing I'm going to do is write a comment to myself. So if we want to write a comment to ourselves, we use the hold shift and the number 3. That's going to give us the comment or pound symbol. You can see that the text is green. I'm going to type intro to R, and then I'm going to give myself, click the enter tab, and we're going to give myself a little bit of space, move down to line 2, and then I'm going to type what is the console. So what is the console? Well, the console is the bottom left-hand portion of our screen. So this is where we're actually going to be doing all of the computation. So we're going to be writing our code in the R script, and then we're going to be actually calculating our the values in the bottom left-hand portion of the screen, which is the console. So the first thing I'm going to do is work with a couple arithmetic examples. So let's just start off with a very basic example, 2 plus 2. So you can see that when I type 2 plus 2, we don't immediately get an answer. We have to actually run our script, our code, in order to see what the answer is. So if you want to run code in R, there's a couple things you can do. First of all, you want to put your cursor on the line of code that we would like to run, and then you can click the run button, which you can see right here. And when I click run, we can see that in the console, our calculation is being conducted, where we have our code in blue text, 2 plus 2, and then our output, which is going to be in black text. So we see that 2 plus 2 obviously equals 4. So the first way that I showed you how to run code is to click the Run tab, but I can also use another keyboard shortcut. If you're working with a PC, you can hold Control and Enter at the same time. And you can see that we, again, do the 2 plus 2 equation and get an output of 4. So the two ways of running code in R that are very simple are putting your cursor on the line, clicking run, or you can put your cursor on the line and hit Control and Enter, and we get this. Obviously, we get the same answer. So I'll move on to my second arithmetic example. I'll do 6 times 6. So if you want to use the multiplication symbol in R, that's going to be an asterisk. So that'll be holding shift and the number 8. We get a little asterisk symbol, which signifies a multiplication symbol. And we can hold Control and Enter on line 5. And we can see that 6 times 6 indeed equals 36. And then I'll move on to a little bit more of a complicated example. We'll do 10 times 5 in parentheses, and then we'll add 5. So again, in R, the same PEMDAS principles apply. We're going to do all the calculations in the parentheses first, and then we'll work outside of the parentheses. So we can run 10 times 5 plus 5, and I can click run, and we see that we get an answer of 55. So those are just some basic arithmetic examples that are particularly important. But as you can tell, when we ran code in all of these examples, we put our cursor on the line and clicked run, or we held Control and Enter. But something that can be a little bit quicker, especially if we have very long R scripts, and it's very common that a professional data scientist will have R scripts that are hundreds of lines, if not thousands of lines of code. Obviously, you're not going to want to click run 100 or 1,000 times. Something that's much quicker and more convenient is that you can actually highlight all of your lines of code of interest that you would like to run. You can hold Control and Enter, and you get all of those calculations being conducted again. Or you can, again, highlight all of your code, and you can click run. And you can see that all those same calculations are being conducted again. So just another topic I'd like to mention is that when you have code that's commented out in green, you can see that we're not, it shows up in the R console, but R is not actually running any of the code that's commented out when it's in green text. It'll show up in your console, but it's not actually doing any calculations. So now we're going to move on to another section of today's course. I'm actually going to give myself a little bit of space in the console. You can see we've done a couple different calculations, but I want to give myself a little bit of space. So I can actually click the Enter or the Tab, and we can see that we get a little bit more space, which helps my R console to be a little bit less cluttered. So now I'm going to move on to another section in today's course, which is going to be called What is the Environment? So what is the environment? Well, that's going to be the top right-hand portion of the screen. This is where we're going to store our objects. So if you're not familiar, R is an object-oriented programming language, which essentially means that we're going to signify certain values or equations or functions and store them as objects. So objects or phrases are going to symbolize numerical expressions. So what I'm going to do is I'm going to start off by creating an object called year, and I'm going to set it equal to, and you can tell that to set something equal, set an object equal to a certain value, we're going to use the less than sign followed by a dash. So it's this little arrow. I can use the equation, the equal sign, but we're not going to cover this topic in today's class, but you'll see in later classes that when you use a double equal sign, that can a single equal sign and a double equal sign will mean different things. So I think it's more applicable if you want to set an object equals to a certain value to use the less than symbol followed by a dash. So currently I'm working in the year 2022. So I'm just going to type 2022 on line 10, going to click run. And then you can see in my R environment, there's an object called year set equal to 2022. And then I'll create another object. This time it'll be states. So I'll set states equal to the number 50. There are 50 states in the United States. And I can click run for line 11. And we can see that in our R environment, this object called states is being created and stored here. It's equal to the number 50. And then we will create an object called Dylan's age. My name is Dylan. I'm a little bit over 30 years of age. So I will create an object called Dylan's age, and I'll set it equal to 30.2. I can hold Control and Enter, and we can see that in our R environment, there's an object being created called Dylan's age that's equal to 30.2. So now I've been demonstrating how these values are being stored in the R environment, but we can also print out these values to actually see what they're equal to. So if I want to print out a value, I can go into my R script. I can, for example, work with the first object, which is called year, and I can just run line 14, year, and we can see in our console that the year object is equal to 2022. So when we just run a line of code that has our object with it, we actually just print out the value. We can do the same thing for states. We can click run, and we see that the states object is equal to 50. And lastly, let's work with Dylan's age. So you can see that when we actually type Dylan's age, there's this little purple tag that shows up. So I can click Dylan's age. So it already understands that there's an object called Dylan's age. I can click on it, and I can hold Control and Enter, and we can see that an object indeed exists called Dylan's age, and it's equal to 30.2. So moving on to the next section of this class, which will be called What are types of data? So there are a couple different types of data that can be understood in R. First of all, we have numeric data that are numbers, and then we can also have character data, which can be symbols or letters. So let's start off by working with numeric and integer data. So I'll write a comment to myself, which will entitle this section of the code called numeric and integer data. So let's say I want to understand how R is interpreting the object called year. So I will in order to do that, I'm going to use the class function. So first of all, I'll type out the word class, and then we can see that R understands that there's a function called class. Class stands for classification. I can click the class function, and then we can see that R will place an open and a closed parentheses. So the function is labeled by class, and then we have the object which will be interpreted through our function within the parentheses. So let's say I want to find the classification of year. So I will type class and then year within the parentheses. And if I run that line of code, we can see that R is interpreting the object called year as a numeric variable, which is convenient because year is a numeric variable called signifying the number 2022. But let's say I want to understand how R is interpreting the object called Dylan's age. So again, I can use the classification function and I can type Dylan's age. Again, R already understands that I want Dylan's age. I can click Dylan's age. And then if I hold Control and Enter, we can see that R is interpreting Dylan's age as a numeric variable, which is convenient because Dylan's age is a numeric variable. It's equal to 30.2. So let's say I wanted to convert Dylan's age not from a numeric variable to an integer variable. So in order to do that, I can type Dylan's age, and then I can set it equal to an integer by using the as.integer function. So there's a function called as.integer, which converts numeric variables to integers. So I'm going to type as.integer, and then I'm going to type in Dylan's age. So we originally set Dylan's age to 30.2, but now we're going to convert it to an integer where we're going to, again, type Dylan's age, Dylan's.age. We're going to rewrite over the original 30.2, and hopefully it will turn Dylan's age into an integer. So if I run that line of code and then I type Dylan's age, we can see that Dylan's age is now equal to 30. So it actually rounded down for us because we wanted to change that numeric variable that had a decimal place in it into a whole number or an integer. So it rounded down from 30.2 all the way to 30, which is convenient. So now if I look at the classification of Dylan's age, we can see that R is no longer interpreting Dylan's age as a numeric variable. It's interpreting it as an integer. So it's a whole number now. So it looks like we've made pretty good progress. So I think it'd be probably an appropriate time to save our R script. So in order to save an R script in RStudio, I'm going to click File. I'm going to move down to Save As. And then we can see that we have a save window opened up, and I'm going to save this as Class 1, Florida Data Science Academy, FDSA, and I click Save, and then our R script changes from Untitled to Class 1 FDSA. So that's great, and now I'd like to move on to the next section in our code, which is going to be entitled Characters and Vectors. So previously, we've been working with numeric and integer data, but we can also work with characters, which are letters and phrases, and vectors, which are objects that store multiple different elements as a single object. So let's start off by creating an object called name. We'll set it equal to a character called Dylan. So as you probably know, my name is Dylan. And this character element is being designated in green text, signified by quotation marks. So if you want to create a character element in R, always use quotations. You can either use a single quotation or a double quotation, and that will turn your text green. And that signifies that R is understanding this as a character element. So if I run line 32, we see that in our R environment, there's an object called name, and it's set equal to the phrase Dylan.
And if I wanted to look at the classification of name, we see that the object called name is being understood as a character element. So that's what we intended. So we're on the right track. So let's say I wanted to rewrite over the object called name. So I'm going to create a new object called name, which will write over the previous object that's equates to Dylan. But I want to set it to equal to all of the letters in the name Dylan. So in order to combine multiple different elements to be stored as one unique vector, I'm going to use the concatenate function, which is signified by a C and then open and close brackets. So we have this C concatenate function, and I'm going to type all of the letters of the name Dylan. So we have a D, a Y, an L, an A, as well as an N. So we have 5 different elements here. Each one of them are signified uniquely within quotations, and then they're all spaced with commas. So if I run that line of code, and then we take a look at the object called name, we see that name is equal to 5 different elements, D, Y, L, A, and N. We can also look in our environment, and we can tell that name is a character vector signified by the C, H, and R, standing for character. And then vectors in R are signified by brackets. So this one means that we have one vector that's constituted by 5 different elements, D, Y, L, A, and N. And let's say if I wanted to look at the classification of name, we note that R is interpreting the object called name as a character vector. We can also look at the structure of name. So we use the str function. That's somewhat similar to, well, actually not too, well, it's relatively similar to the classification function, but it gives us a little bit more information, and you'll see here. So as you can tell, structure does demonstrate what type of data type it is. So name is a character element, and it's actually a vector because we have 5 separate elements that are being stored as one unique object. So classification gives you the general understanding of what kind of data type it is, but structure gives the data type as well as lets you look a little bit further under the hood and gives you a little bit more information. So that's our section on character vectors, but let's work with numeric vectors. So we've worked with numeric variables, but we haven't stored them as unique vectors. So we'll start off by creating an element called years. We had an element previously that was year that was set equal to 2022, but now we want an object called years that is equal to many different years. So we're going to have years is going to be equal to all of the years that I've been alive. So I was born in 1992, and the current year is 2022. So if we want to create a vector that's equal to all of the years from 1992 to 2022, we type the first year and then separated by a colon, and then we put the last year in our sequence. So if we run that line, we see an object opens up in our environment. It looks like we have a lot of different years, but to look at them in more detail, I'll type out years, and we find that years is actually equal to each unique integer from 1990 to all the way to 2022, and that's exactly what I intended. These are all of the years that I've been alive. R did a good job at finding that answer. So, but let's say I wanted to create an object called years that isn't equal to every year that I've been alive. Let's say I just want to have years be equal to specific years that would be relevant to a given data analysis. So let's say I'll create an object called years. I will set it equal to, let's say I just want my birth year, 1992, the year 2000, and then the current year, 2022. So again, we're using this concatenate function, and then we have 3 separate elements that are separated by commas. And unlike the the character section, I'm not separating these elements by with quotations because we don't want them to be understood as character elements. We want them to be understood as numeric variables. So we're not using quotations, but we are separating them by commas. And we can run that line, and then we can type out years. And we see that R has written over the previous object called the years, which is equal to all the integers from 1992 to 2022. Now we have a new object called years that's only equal to the 3 specific years that I wanted it to be equal to, which were 1992, 2000, and the year 2022. So that's just an example of how we create numeric vectors in R. But now I'd like to move on and create a new section, which will be called Working with Numeric Vectors. So it's not enough just to create numeric vectors. We actually have to do certain data analyses in order to create informative analytical insights. So let's say I'm a teacher at an elementary school, and I have 5 students in my class, and I'm just documenting all of the grades I'm documenting the grades that were in my class. So of maybe a previous test. So I'll create an object called the grades, and I'll use the concatenate function. And the grade, I have 5 students, and the grades that they got in this test were a 70, a 75, a 72, a 74, and an 80. So this object called grades will be equal to 5 separate, a vector of 5 numerical elements, and I'll run that. And then we can take a look at grades. And indeed, we have a vector constituted by 5 separate numerical elements. But let's say I wasn't too happy with the grades that my students got on this test, and maybe I implemented a new curriculum or a new study guide to help them out on the next test. So I'll create a new object called new grades. And let's say all of the students did much better on this test, and they got increase their grades by 5 percentage points. So let's say I wanted to increase, just add 5 percentage points to each one of the unique elements of the object called grades. So I'll do that by typing grades and simply adding 5. And if I run that line and then type out new grades, again, R already understands that there's an object called new grades, so I can just click enter and new grades pops up. And if I run that line, we see that R successfully added 5 percentage points to each one of the elements in grades. So a 70 is now a 75, a 75 is now an 80, and so on. So that's just a basic example of how we do some basic arithmetic and work with numeric vectors in R. But we can also do a little bit more complicated examples. Let's say I want to create an object called newer grades. So say I implemented another study guide or new curriculum, and I want to add 10%. I want to add 10% to the grades from the original assignment. So I'm going to type grades, and then I'm going to add 10% to each one of the previous grades. So I have the original object called grades, and then I'm adding 10% from their previous test. So I want them to increase their grades by 10%. And if I run that line, and then I type out newer grades, we see that R successfully added 10% to each one of the original objects called grades. So a 70 is now a 77, a 75 has increased all the way to an 82.5. The third grade was a 72, that's now a 79.2, and so on. So that's just another example of doing some basic arithmetic, a little bit more complicated than our original example, but still important. So now we'll be moving on to another section in this course, which will be called Logical Operators and Basic Functions. So we've already worked with some basic functions. We're going to add teach you guys a few more, but logical operators you can think of as kind of true or false statements. So let's start off with an example that I think will better exemplify what I'm talking about. So let's say I have 10 greater than 8, okay? So obviously, I'm sure you guys know that 10 is greater than 8. But we can use certain logical operators. These are going to be things such as equal signs, greater than, less than symbols, greater than or equal to symbols, and they're going to produce true or false statements for us, which will be quite helpful when we develop more of our programming and analytical skills. So let's just run the line 10 greater than 8. And when we run that line, we see that we get a true statement. So that's very obvious, but it's important basic concept to understand how we work with greater than or equal, greater than or less than symbols, and that they produce these true or false statements. And I can start off with, give you another example. Let's try 8 greater than 10. Obviously, 8 is not greater than 10, so we should get a false statement. So if we run line 64, indeed, we do get a false statement. So those are some basic examples, but let's build on that by writing some more complicated logical statements. So let's try, let's find the sum of grades. In order to find sum, we can use there's actually a function called sum. So we type out sum, and then I want to find the sum of grades. So that's that original vector that we created that's constituted by 5 separate elements. And if we want to find out if the sum of grades is greater than the sum of new grades. So new grades is when we added, I believe, 5 percentage points to all of the original grades. So this should be false. The sum of grades should actually be less than the sum of new grades. So let's see if we get a false statement. And indeed, we do get a false statement. So if we want to find out if the sum of a certain vector is greater than or less than the sum of another vector, we can use these logical operators, these less than or greater than symbols, in order to find those answers. So let's try another example. We'll also add another basic function. We're going to use the mean function. So if we want to find the average value of a vector, so we're going to type mean, and then we're going to put our object grades within the function. And we want to find out if the mean of the vector called grades is less than the sum of the vector called new grades. So when we run that line of code, we get a true. So those are just some basic examples of how we can use logical operators to find if certain statements are true or false within RStudio. But it's also important to note that true and false statements are actually associated with ones and zeros. And this can get a little bit more complicated, but is an important concept when you develop more of your analytical skills. So I'll just write another section in my code that says true and false are associated with 1 and 0. That might sound kind of confusing, but I'll give you a couple examples that will demonstrate what I'm talking about. So let's say I'm going to create a statement, an object called statement 1, and I'm going to set it equal to the mean of grades less than the sum of new grades. So we actually ran this logical statement earlier. The mean of grades indeed is less than the sum of new grades. So you're probably thinking, okay, this is going to produce a true statement, which it will. But what I'm trying to demonstrate to you is a true in R is also understood as the value 1. So let's say I run that line, and all right, so now I'm going to actually add a true statement to a true statement. So we should actually get the number 2, which may seem kind of confusing, but if I add this statement 1, which is true, because the mean of grades indeed is less than the sum of new grades, and I add it to itself, so if I have statement 1 plus statement 1, and I run that line of code, we actually get a value of 2. So that just demonstrates to you how true statements in R are actually understood as values of, as ones, and false statements are understood as the value 0. And now let's work with a false statement. We'll create a statement 2, and then we will set it equal to the sum of grades greater than the sum of new grades. So I think we ran that earlier. The sum of grades is not greater than the sum of new grades. So we should get a false statement. And indeed, we see in our environment, we get a false statement. But now let's try doing some arithmetic with true and false statements. So if I have statement 2, and then I add it to statement 2, I should get a 0. And indeed, we do get a 0. So if we actually can do arithmetic with true and false statements, which is kind of convenient. Let's do one more example. If I have statement 1, and then I add it to statement 2, so a true statement plus a false statement, hopefully I get a 1 because 1 plus 0 is 1. And indeed, we get a 1. So I just wanted to give you that little tutorial demonstrating how true and false statements are actually associated with 1s and 0s in RStudio. And now I'll create a new section in my code, which is going to be entitled More Logical Statements. So I'll just give you a couple more examples of how we can use some other symbols when we're working with logical statements. So let's try the logical statement if 10 is equal to 8. So an important concept in the R programming language and its syntax is that when if you want to use a logical statement to determine if something is true or false, and you want to use an equal sign, you actually have to put 2 equal signs together. So you can't have, if I wanted to find out if 10 is equal to 8, and if I run that line, we get an error because R thinks that you're setting the value 8 to equal 10 as if you're creating a new object. So let's say I created an object called 10 and then I set it equal to 8. You can see that in our environment, the object 10 is equal to 8, but that's not what I'm trying to do. I'm trying to determine if I'm trying to use a logical statement, a logical operator, to create a true or false statement. So if I want to do that, I need to use a double equal sign. So I'm going to use 10 double equal sign equal to 8, and hopefully I get a false. Indeed, we do get a false. That's what I was trying to demonstrate to you guys. Let's try another one. Let's use a greater than or equals, greater than or equal to symbol. So if we want to use greater than or equal to, we start with the greater than, and then we use the equal sign afterwards. So is 10 greater than or equal to 8? Hopefully we get a true statement there. Indeed, that does produce a true. And then we'll use one more example of a less than or equal to symbol. So less than equal to 10 is less than or equal to 8. Hopefully we get a false statement. And indeed, we get a false statement. So just a couple more examples of working with logical statements. So if you want to find if something is equal to something else in a true or false context, you have to use the double equal sign. And now we'll create another section that will be entitled More Basic Functions. So we've already worked with a sum and mean, but now let's try to work with square roots. So how do we find the square root of a given object? Well, we can start off by creating an object that's called square.root val, square root value, and we'll set it equal to, so let's say we're trying to find the square root of that original object called the grades. So we're going to use the square root function. That function is designated by sqrt, and then we're going to open up our parentheses, and then we're going to type in grades, and hopefully this will be able to find the square root of grades. And if we type out that value, square root val, and click enter, we find that R was able to actually didn't find the square root of all of the grades summed together. It found the square root of each unique element within grades. But let's say I wanted to find the square root of the summed value of grades. So I can do that by, well, we'll create an object first called square of sum. And we'll set it equal to the square root of the sum of grades. So an important concept when you're working in R with multiple different functions is that you work in, out. So first we're going to find the sum of grades, and that's within the interior of the parentheses, and then we move out to the exterior, and then we're going to find the square root of that summed value. So first, we're going to find the sum of grades. In fact, I can just actually highlight this little object here and run that. So we're trying to find the square root of 371. So if I run that line, and then we can type out square of sum, we see that the square root of 371 is 19.26. So I just wanted to demonstrate to you guys to show you that when you can use multiple different functions within one line of code in R, but R will always work in, out. So if you want to find the square root of a summed value, first you start with the sum, and then you put the square root symbol on the exterior. So something that I like to incorporate in the Florida Data Science Academy classes is that we have in-class assignments. So generally within each class, we'll have 2 in-class assignments where I'll give you guys a question that reflects a lot of the things that we learned throughout the class. Then you can pause the video, you can work on that question. Hopefully it takes about 5 to 10 minutes, and then you can resume the video and click play and see if your answers match up to the answers that I'll give you guys. So I'll start a new section in my code, which will be called in-class assignment. And then, so I'll verbally tell you guys the assignment, but I'll also write it down for all of us. So I want you to create an object named profits, consisting of 5 numbers, which are 20, 15, 30, 40, and 50. And then I would like you to multiply profits by 3 and save this new object as new profits. And then lastly, I would like you to find what is each object in new profits and what is the sum of your new object called new profits. Okay, so in conclusion, I'd like you to create an object named profits consisting of 5 numbers, which are 20, 15, 30, 40, and 50. And then I would like you to multiply this object called profits by 3 and save it as a new object called new profits. And then lastly, I want you to find what is each object in new profits and what is the sum of your new object called new profits. So you can pause the video, work on that question, and then resume the video, and I will give you the answer. Thanks. Hi guys, welcome back. So hopefully you were able to successfully find profits and new profits, and I think we should start off by creating an object called profits. We will set it equal to 20, 15, 30, 40, and 50. So we can run that, and then we can see that in our our environment, we have an object called profits. And then I would like you to create a new object called new profits. And I wanted you to multiply profits by 3, and hopefully we get a new object called new profits, and we can see that pops up in our environment. And then lastly, I wanted you to find the sum of new profits, which is 465. So those are the answers to the first in-class assignment. Hopefully you guys were able to do that, find profits and create a new object called new profits by multiplying profits by 3 and then finding the sum of new profits. So now we'll be moving on to our second in-class assignment. And we have a different question for you, which is, I want you to create a vector named height, ranging from 50 to 80. And then I would like you to find the mean, the standard deviation of height, the mean and standard deviation of height. And then lastly, I'd like you to find the square root of the sum of all heights. So in synopsis, I would like you to create a vector named height ranging from 50 to 80. So you're going to have, I guess, 31 different unique values within height. And then I wanted you to find the mean and the standard deviation of height. And then lastly, I want you to find the square root of the sum of all of the heights. So I think I put in one question that we actually didn't work on in class, which is the standard deviation function. So I think I did that for a particular reason, which is that an important concept to being a good data scientist is that you have to be comfortable looking up certain functions that maybe you're not familiar with, and you have to get comfortable at using the internet in order to find some of the answers that you don't know how to compute in RStudio. So most of these functions we've already worked with, but I do want you to look up how to find the standard deviation of an object in R. Hopefully you guys will be able to do that, but we already have worked with mean, square root, and sums and creating vectors. So those will all be easy, but hopefully you will also be able to look up how to find the standard deviation of an object in R. So hopefully you guys can work on that, and I'll see you soon. Hi guys, and welcome back. So now I will be giving you the answer to the second in-class assignment. So I wanted you to create an object called height, and it was set equal to all the integers from 50 to 80. Again, we're going to start our vector with the first number, and then we're going to use a colon, and then we're going to place our last integer after the colon, so we can run that. Then I wanted you to find the mean of height, use the mean function. We see that the mean of those values is 65. And then hopefully you were successfully able to find the standard deviation function, which is simply SD, very easy. So we find the standard deviation of height, and we see that the standard deviation of height is 9.09. And then lastly, I wanted you to find the square root of the sum of all the heights. I believe we worked on that on line 91. And so in order to do that, we write the square root function followed by the sum of height. Again, we work in to out. So we start off by finding the sum of height, and then lastly, we're going to find the square root of the summed height value. And then we can see that the square root of the sum of height is 44.8. So that concludes our second in-class assignment, and actually concludes our entire first class of the 24-part series of Introduction to Data Science with Florida Data Science Academy. I hope you guys enjoyed this class, and I'll look forward to working with you in part 2. Thank you.